Welcome back. So, in previous lecture mainly we discussed about how to identify or locate the epicenter of different earthquakes. So, if you are having 3 stations maximum, you can identify or locate the epicenter of any particular earthquake. And then we also discussed about that what are the symbols what we are talking about, the pitch and ball diagrams, which are indicating of different faulting. So, we have normal fault, reverse fault, and the strike slip fault. So, I will not go into the detail of the faults which have been given here, but to just have a brief introduction about this. In this case, what we see is an extension when the hanging wall on the left hand side moves down along the inclined fault plane, and in case of the reverse fault, the hanging wall moves up in case of along the fault plane, inclined fault plane. So, this is in compressional tectonic environment, this is an extensional tectonic environment, and whereas this one, the third one, is in strike slip fault, where one block moves away from or just past each other with respect to the fault line here. So, in this case, what we see is the right hand side block is moving towards us and the left hand side is moving away from us. So, this is we term as an right lateral strike slip. About the features, what we see on the surface, we will talk when we will start talking about the active faults and active fault topography, and the respective symbols are been given here. So, usually in the map after the earthquake, such figures or the symbols will be available, which indicates that what type of earthquake. Now, moving further, we also had brief discussion about that the earthquakes, distribution of the earthquakes, and now coming to the recurrence of earthquake due to stress developed by tectonic forces. Now, this before getting into the example of 2001 Bhuj earthquake, I will just briefly tell you that what are the reasons for the triggered earthquakes or the triggered stresses on different faults because of an earthquake. So, triggered stresses mainly we say that the small part of stresses are released which were accumulated slowly when the Earth's plate moved towards or past each other. So, this also indicate that not all the stress or the energy which was been accumulated got released during a single event, but there is some left out stress which can trigger the earthquake in near future, or you can say that the release of energy on a particular fault has triggered the earthquake on another one. So, usually this has been taken into consideration that if a stress is released on a particular fault during a particular earthquake, then there will be a drop in stress on that particular fault. So, that means that the next earthquake on that fault will not reoccur until this stress rebuilds and it crosses the threshold limit. And typically the time duration which has been taken to rebuild the stress may vary from hundreds to thousands of years. So, in case of the areas which are close to the plate boundaries will have lesser interval or that the recurrence interval, whereas the areas which are sitting away from the plate boundary will have the larger recurrence interval. So, this is usually has been considered that once the earthquake has occurred on a particular fault, then there will be a drop in stress pattern, but and it will remain quiet until the next event, because this requires the rebuilding of the stress on that particular fault. But an earthquake will occur elsewhere at the site other than the slip fault. So, in this case, what we can conclude is that though the earthquake has occurred in particular area, for example, in one of the slide I was talking about that there was 1905 earthquake, then there was 1934, and then we had 1950. This is in case of Himalayas. So we what we discussed in during that time was that this portion, which has not triggered any earthquake, will form will indicate a sort of a seismic gap. But it is quite possible that this earthquake was triggered on one of the fault system which exists in the region, and the another fault system which is sitting in that particular area can host an earthquake. So this what has been discussed here, that the earthquake will reoccur elsewhere and not on the particular fault, but the area may be the same. So the area where the stress is building up will be the site for the next earthquakes to occur, both as small as well as the large one. Now, in case of the recent earthquake of 2001 Bhuj earthquake, what we observed was, of course, the concentration of the earthquakes, that is the aftershocks, were confined to this region, and that indicate the rupture area, but there was sudden increase in the seismicity in this particular region. Okay. So earthquake was triggered here, but we saw that number of earthquakes, small magnitude earthquakes, micro earthquakes were triggered, and few small magnitude earthquakes which were greater than 5 were triggered further north along, could be along the two active faults which are named as Gedi fault and South Wagad fault. So probably the stress which was released here has triggered the stress which was accumulated in this area, and this may host another earthquake, a large magnitude earthquake, which we will call as a triggered earthquake. And similar phenomena was been observed in 2015 earthquake, which was along the Himalayan region, that was in Gorkha earthquake. So 2015 was one, and then immediately after a month another earthquake was been triggered, which was of similar magnitude. And so some scientific groups, they consider that earthquake as an aftershock, but that could be a result of a triggered stress on another fault or on the same fault which was left out. That is, the stress which was left out might have triggered the another earthquake in that region. So sometime because of the large earthquake, another large earthquake could be triggered in the nearby area. So this part we have already discussed, so I'll just move quickly. So locating the fault, in which direction it is dipping and which whole area was ruptured, this has been shown in this diagram. This is a plan view which shows the distribution of the main shock or location of the main shock and distribution of the microseismicity or the aftershocks, and this has been shown with respect to again the plan view and the depth which has been plotted. So this shows that the main shock was triggered at around 25 or 23 to 25 kilometer deep, and probably was along the North Wagad fault, which is dipping due south. But in some cases it has been observed that probably this is not the actual plane, because this is an arbitrary line which has been drawn, but could be the the earthquake was on the Kutch mainland fault. Now, the classification of the earthquakes on the basis of the focal depth, this we have been talking about that intermediate and shallow and deep earthquakes we discussed when we were talking about the plate tectonics. So, the focal depth of an earthquake is the depth from the earth's surface to the region where the earthquake's energy originates. So, this is the point of the focus, and exactly on the surface this point has been termed as epicenter. So, most of the earthquake occur in the brittle portion of the crust above the brittle ductile boundary, that is the boundary between lithosphere and asthenosphere. So, in terms of the depth, if we have to classify the in the broader sense, then up to 70 kilometer depth we classify those earthquakes as shallow earthquakes with depth ranging from 70 to 300 kilometers, then intermediate, and deeper earthquakes are having the depth more than 300 to 700 kilometers. So, to this you can refer with the figure which was been shown as in the case of the Wadati-Benioff zone, which explains that the whole subducting plate will host the earthquakes, and depending on the depth you can classify those earthquakes, either they are deep earthquakes, they are intermediate or shallow earthquakes. Now, we discussed about the seismic waves, we discussed about the earthquake epicenter, which is of course, these are the two important parameters, and in one lecture we talked about the details of the lithology, which plays an important role in terms of seismic shaking. So, after having a brief understanding of the occurrence of the earthquakes, the depth of the earthquakes, then the type of faulting, the geology also plays an important role in seismic hazard. So, if you have the different lithology, for example, it has been shown here that on the left you have hard rocks, igneous rocks, or either you can say it is a massive rocks if you are having, then you are having sedimentary rocks, and then alluvium, and then further finer alluvium here. So, the amplification during ground shaking will vary from place to place. So, hard rock will have less amplification, and it keep increasing if you move towards the loose material, and in sedimentary rock area you will have comparatively higher amplification because of ground, because of the seismic shaking, and here in the case of the alluvium you will have much larger as compared to the sedimentary rocks and the massive rocks if you are having. So, the ground acceleration is very much dependent on the type of sediments and rock types. So, this effect basically is been termed as material amplification. So, along with the understanding that where exactly our sites are located, or site of our interest, or any urban settlement is located, whether it is on sedimentary rock, igneous or metamorphic rock, or you are sitting on alluvium, depending on that you will have the amplification during the ground shaking. Now, getting into the further detail of the seismic wave and its relation with the amplification, the frequency of seismic waves when the earthquake is triggered, variety of different frequency of seismic waves are generated. So, the frequency of seismic wave, that is body wave, and you are having the surface waves, plays a key role in damage pattern. So, this part is the most important one, and this will again depend on the geology of the material, okay. That is the geology of the area, what type of material we have at a particular site. So, again along with that is one the part of the geology, but along with that we have that how far the site is located from the epicenter, okay. Whether it is close or within the zone, or it is sitting far away from the epicentral zone. So, most P and S wave, that is your body waves, have frequencies ranging from 0.5 to 20 hertz, and whereas the surface wave we have the frequency less than 1 hertz. Okay. So, we have the frequencies which are ranging from 0.5 to 20 hertz we will be able to experience during any particular earthquake. So, and during any earthquake, both body waves and P surface waves will be generated. So, during earthquake, wide range of frequencies of seismic waves are produced. So, shaking resulted by high frequency wave, which are 0.5 to 20 hertz, that is your body waves, and this waves will cause shortened buildings to vibrate. So, if you are having low story buildings, they will vibrate during the body waves which are generated. So, and the low frequency waves usually your less than 1 hertz. So, in this case what we are having mainly the surface waves, and this surface waves will cause high buildings to vibrate. So, in this case what we can conclude is both shorter building as well as the taller buildings will vibrate, because both body waves and surface waves will be generated during a particular earthquake. So, it is the shaking or vibration usually causes the damage to the civil structures. Now, near epicenter, both frequencies, so you have the body wave and the surface wave, both frequencies high and low will be experienced, hence both shorter as well as the taller buildings will be damaged. So, this is in case of the epicentral region. While the increasing distance, higher frequency will mostly the P and S waves. So, this will get weakened and this will die out at an increasing distance, and this process is termed as attenuation. But the low frequency waves, usually what we have, like in case of the surface waves, that is L and P waves, will have tendency to travel long distance without much of attenuation, and this will cause damage to taller buildings which are located far off. So, what basic thing which we learn, the fundamental thing we learn, that in case of your epicentral area, you will experience both, that is the low frequency waves and high frequency waves, as the body wave and surface waves, and that will result into the damage of shorter building and taller buildings. So, those will be those buildings, both shorter and taller, will be experiencing vibration, whereas the far distance located areas, mostly the low frequency waves will travel without any attenuation and result into the vibration of the taller buildings. So, these are some catastrophic events which have been listed here right up to 2010, but we also had the recent earthquake, as I was talking about, 2015 in Himalayas. Now, frequency and building vibration, if we consider this too, buildings of different height sway at different frequency like inverted pendulum. So, if you are having the shorter buildings, they will sway less, whereas if you are having the taller buildings, they will sway or swing, we can say, and the larger area has been covered. Okay. So, this is the comparison which has been given for the shorter building, mid height buildings and taller buildings. So, buildings with 1 or 2 story building oscillates at 5 to 10 hertz, shakes back and forth rapidly with a high frequency. That is the period of, this is basically what we are talking about, the sway period which is around 0.2 second to 1 second, whereas in the case of this one, this will be higher, and in case of this one, that is here taller buildings, it will be comparatively higher. So, mostly if you are having the buildings which are having the open story, okay, and the ground story is an open story, or we can say on just on the columns, they will have chances of getting damage very soon, okay, because the movement will result into the sway of the building. So, if they are been tied up by these members, then the diagonal members, then they may stay or withstand the earthquake ground shaking. But if you are having this type of buildings, in most of the cities we see that the ground floor has been used for garages, okay, and that will result into the collapse of this portion. Similarly, if you are having the two rigid portions of the building, and in between you are having many windows, and those regions will also act as a weak zone and will result into the damage, okay. So, a weak zone, a weak ground floor without diagonal braces will result into failure, and this is the example of that, the collapse of the ground floor, which are unbraced ground floor garages, very much similar to what has been shown here. So, this is another case of the many windows which have been located here in between the two massive portion of the building, and whereas this did not suffer anything because this was all having the walls here, not just the columns. So, the weaker floor was this which collapsed. So, in most of the areas there is a retrofit has been done, putting the diagonal braces to withstand the earthquake shaking in this fashion. So, of course, this is not very aesthetic in the sense of the beauty of the building, but the most important is to save this building from an earthquake, because again this whole area is with windows. So, this diagonal braces will act as a protector during the ground shaking. Some few more examples which shows the strengthening of houses, which can be done easily with diagonal braces and sheet ply. If you are having wooden houses, then you can use the diagonal braces which can support this whole wall, as well as you can use the plywoods or the wooden sheets to protect all this, okay. Otherwise, if you have just clamped, then there are chances of crumpling of these two columns here, and these two members will be damaged, and the same is in case of this one, okay. But if you have applied the diagonal braces or the ply, then you can safeguard the structure. Now, with the more development in terms of the seismic safety, many countries, including India in some places, have started using the shock absorbers for the building, and this is what we call the base isolation pads, which permits a building to shake less than the violent shaking of the ground. So, usually this has been comprised of lead, and this portion is of a rubber base which have been put at the base of the building. So, building is going to be resting on this, and whenever there is a big event, this component or this portion or the member will absorb the ground shaking. So, this is a case which has been shown for the area of this very important building in San Francisco. Okay. Now, another issue usually has been faced, that as we discussed, that different buildings will sway at different frequency. So, the shorter building will have different sway, the larger one will have different sway, because it will sway larger, much more area will be covered here. So, if you are having these two buildings sitting close to one another, then you will have an effect what is we call the ponding effect, and that will also result into the damage. So, similar this was from 1985 Mexican City earthquake, where the two building with the different, that is shorter was the rigid, and the taller one was more flexible, they collapsed. Okay, and they have, because they sway at different frequency and they collide during an earthquake. So, this was an example from 1985 Mexican City, and similar example, but fortunately it did not damage. But what we see here is that this is a shorter building, this is a taller one, and they have almost collided along this point here, and this was from 2015 Gorkha earthquake in Nepal. So, I end here with this lecture, and will continue in the next one.